finite impulse response filter design. Let's start with an ideal low pass filter. In an ideal low pass filter, we have two different problems associated with that. First one is its impulse response will be of infinitely long. The other problem is it's a non-causal system. Let's take this ideal low pass filter, which is one for frequency from minus omega c to omega c and whose gain is 0 for other frequencies. If we take the DTFT of this, we'll be getting an impulse response of the filter of this ideal low pass filter. This is the we have applied the DTFT after applying the formula of the this is the inverse DTFT. This is the from here to here we are getting it by applying I D T F, so inverse DTFT. Anyway, so we are getting this sinc function after solving, and that is for all values of n is from infinity to infinity, minus infinity to infinity. So this ideal low pass filter, okay, which is some kind of brick wall structure, the impulse response after taking inverse DTFT is this, and here you can see it's a sinc function and it's starting from minus infinity basically and it's going till infinity. And so the problem is it's an infinitely long sequence, and since this is both sided, you can say it's a non-causal also, and non-causal systems cannot be implemented, cannot be realized. So how can we overcome this issue? We'll discuss this in the next slide. What we can just limit the number of samples. Instead of taking infinite number of samples, we'll just multiply that impulse response with a rectangular window whose magnitude is 1 in the passband, you can say, and this window is will be in the time domain only. Basically, multiplying with a rectangular window is equivalent to just taking finite number of samples, or it's equivalent to truncating the impulse response from both sides. So let's see some steps involved in the design of an FiR filter using window. We can start with an ideal filter, okay, and whose frequency response is h omega. Then we'll take the inverse DTFT of that to obtain h omega, and this h omega will be double-sided, infinitely long as well as non-causal. Therefore it cannot be realized, it is unrealizable. Then what we'll do, we'll just truncate this hn with a window function, say a rectangular window, and that window will give us only say m plus 1 number of samples of this window, or you can say m plus 1 number of coefficients of hn. The other coefficients of hn is discarded. Okay, so now we have finite length of the impulse response and we are calling it htn. However, this htn is still non-causal because its value, there are some samples whose value is non-zero for n is less than 0. So the other thing is, basically, in order to make it causal from a non-causal, we'll just shift it right by m by 2 number of samples. After shifting it, we'll be getting htn minus m by 2. So after shifting it, this impulse response will become causal as well as stable. So however, this shifting will introduce a phase. Shifting is equivalent to a delay, and delay will introduce a phase factor, and that phase factor is e power minus j m by 2. Okay, so anyway, phase factor is not an issue. In this way, if we are just multiplying a impulse response with a rectangular window, then shifting it right in order to make it causal. In that way, we can make our filter realizable. So let's see a low pass filter. This is our low pass filter, magnitude response for low pass filter, and this is the impulse response mathematically which is obtained in the previous slide. However, this is unrealizable. In order to make it realizable, we have to multiply this function for a rectangular window, or you can say we have to limit this n. Basically, instead of taking from minus infinity to infinity, we'll just take m number of samples, and here you can see this is shifted by m by 2. N is replaced n minus m by 2. So actually the n is from minus m by 2 to m by 2. When n is replaced n minus m by 2, so the n is from 0 to m. However, this sinc function will be in a 0 by 0 form. For that will be for n is equal to m. So just after solving it for this 0 by 0 form, we are getting omega c by pi. So this impulse response is realizable. Okay, so this is our high pass filter design. First, let's see how can we represent a high pass filter in terms of low pass filter. We know that this is a low pass filter and this one is a high pass filter. And this high pass filter can be represented in terms of low pass filter. That is, the high pass filter is nothing, the frequency response of high pass filter is nothing, it's a 1 minus frequency response of the low pass filter. So if you take the inverse Fourier transform, inverse DTFT of this, will be getting impulse response of the high pass, which is equal to delta n. If you take the inverse DTFT of 1, it will be delta n. Okay, and the inverse DTFT of capital H LP will be small h LP. Let me just first clear all these things. So if it means you can represent the impulse response of a high pass filter in terms of the impulse response of a low pass filter. So it is nothing, it is just delta n minus HLP. So just apply, we in the previous slide we have obtained this HLP. So just using this and this, we can obtain this impulse response of a high pass filter, which is equivalent to this. Obviously we know that when n is equal to 0, its value is 1. So when n is not equal to 0, so its value is 0. So therefore you can say when n is not equal to 0, its value, it's introducing only a negative sign because of this. Okay, in the same way we can represent the band pass filter or band stop filter in terms of low pass filter. So band pass filter is equivalent to a low pass filter with a cutoff frequency, say omega c2, and assume that omega c2 is greater than omega c1. So this is the filter, low pass filter with cutoff frequency omega c2. This is a low pass filter with cutoff frequency omega c1. If we subtract the two, we are getting this. It means we can subtract the impulse response of this minus the impulse response of this will be equal to the impulse response of this. So that's the thing we have done. So the impulse response of the band pass filter is nothing, the first impulse response, which is because of this filter, okay, minus this impulse response which is corresponding to this, and similarly for this can be obtained when n is equal to m by 2. Okay, if we have a band pass filter, band stop filter. So it's nothing, 1 minus band pass filter. So once we have obtained the impulse response of band pass filter, which is in the time domain, it will be equal to the delta n minus HBP, because the IDTFT of this will be equal to delta n, and IDTFT of this will be equal to HBP. Okay, some important point. You have seen that after this is our ideal filter, and we have obtained the impulse response, which is ideally containing infinite number of samples, but we have truncated the samples to some finite number of samples. Okay, but this causes a problem actually. When you What you have done, you have taken the ideal low pass filter, then you have taken the inverse DTFT, then from this inverse DTFT, let me just change the color of the pen. From this inverse DTFT, what you have done, we have just truncated the number of samples. We are having now less number of samples. Okay, so if from here to here, if you go back and take the TFT, we are going back into a frequency domain, so you will see that you will be getting this kind of low pass filter. It's not the ideal low pass. This is my ideal low pass, and this is the filter shape you'll be getting. The problem with this, it's not, or the difference of this with the uh, if we compare with the ideal low pass filter, you can see the oscillations here. You can see the oscillations here. You can see oscillations in the stop band. Ideally it should be 0, and here it should be 1. You can see there's a transition bandwidth. So that's the thing, that's the problem will occur in the filter which is realized. Okay, we'll discuss Gibbs phenomena. Now, truncating the impulse response, okay, of an ideal filter, we have obtained a realizable filter. But this truncation causes some oscillatory behavior in the frequency domain, and this is basically a Gibbs phenomenon. So let's check it in the figure. If we are truncating say to 60 number of samples, we are getting this blue one is the frequency response. If we further reduce the number of samples to say 20, in that case this red one is the frequency response. There is a difference between the two is, you can see the number of ripples is more in case if you are taking more number of samples. However, the amplitude of these ripples, blue one for this, is lesser. Okay, let's discuss this one by one. There, this lobe or this lobe is the main lobe basically, and these are the side lobes. Let's discuss this in detail. If we increase the m number of samples, the number of ripples will increase. Okay, you have seen if we increase the m from 20 to 60, so from red to blue, you can see the number of ripples have increased. However, their height has been reduced. So therefore, or you can, oh sorry, the as well as height as well as width. Okay, width as well as height both have been reduced. Okay, the height of the largest ripple remains constant regardless of the filter length. You can say this is the largest ripple. Okay, this is the largest ripple, so the height of these two will remain same. However, the height of the other ripples is reduced. Okay, same thing, as time increases the height of all the ripples decreases. However, the main the largest ripple is not, the height of that ripple is not decreased. Okay, the other observation is, let me just clear this. Okay, the other observation is the main lobe gets narrower as m increases. Okay, that is the drop off becomes sharper. You can see if you look at this main lobe, basically this main lobe, you can see for the blue one, this main lobe is narrower. This main lobe, you can see this main lobe is narrower if you compare it with this, the red one, basically. Okay, so that's one thing about the phenomena. Let's check it for some other point. Basically what we are doing, we are multiplying the ideal filter impulse response with a rectangular window function, okay, which is equivalent to convolving the underlying frequency response with a sinc function. Let's see this. So the truncated sequence impulse response is nothing, the ideal or the desired impulse response multiplied with a window function. Here in our case we have taken a rectangular window function. So in the, if you go in the frequency domain, this will be capital H D, this window function will be capital W, and however this dot, the multiplication will become convolution. Okay, so that's the thing. We want that H T omega to be as close as H D omega, the desired impulse, and this is the ideal impulse response, you can say, sorry, ideal transfer function, and this is the transfer function for this of the filter which we are designing after truncating. So the T indicates truncation. Okay, this is only true, this is equal to this only if the window length is infinite. Window length infinite means Wn is equal to 1 for all values of n. If the Wn is 1 for all values of 1, so this will become a delta function, and convolving a delta function with any function will give the same function. In that case, ht will be equal to hd. However, we have some conflicting requirement. One side we want a narrow window, or we can say we want a lesser number of samples of the impulse response, okay, so that we can have a, the order of the filter should be small. On the other hand, we want that truncated filter should match as closely as the possible ideal filter, okay, ideal filter frequency response. So which in turn is required that the window should be of infinite length. So these two are the conflicting requirement, or you can say there's a trade-off between these 2 points. Let's take an example. I told you that convolution results in the oscillation. Okay, let's take three things. Suppose this is your ideal HD is the ideal filter frequency response, and say this is the frequency response of say rectangular window, and this is the HT says the frequency response of the truncated filter. Okay, let's take this. So this ideal filter is convolved with a Fourier transform of a rect function, and the Fourier transform of a rect function or the window function is a sinc function, you can see here. Okay, so this is a rectangular window frequency response of the Fourier transform of the rectangular window. So at omega is equal to pi, when omega is equal to pi, basically you will see that the overlap, you can see overlap area is very small. However, if you shift this side when omega is lying from omega c to pi, when omega is lying from omega c to pi, so you somewhat the area is again fluctuating, because we are finding the overlapping area between, after multiplying this rectangular pulse with only in this region basically. However, at the edge, you'll be getting something like this. You are multiplying your two functions at this instant and then finding the area, and so on. When your impulse response is, or you can say when your omega is from 0 to omega c, the sinc function is somewhere over here, and then you have multiplied that sinc function with this rectangular function. So then finding the area under the two. In after all those processing for all the values of omega, you'll be getting this kind of function basically. Okay, so that's a resultant thing, and which we are obtaining after convolution between the frequency response of a rectangular window and the ideal low pass filter. Okay, effect of filter length is just plotted over here. Suppose we have taken a filter of 20 of order 20 or 21 number of coefficients. So we are having a 21 number of coefficient here in this filter. You can see if you take the magnitude response using DTFT, so we'll be getting something like this. And so here this width is called the transition width. You can see this width is a transition width. Okay, so it's shown over here, and this is the stop band attenuation, you can see. And the third figure is just plotted. The vertical scale is in dB. Okay, so it's the same plot basically. This and this both are the same. The only difference is this one is with dB scale. Now this is the impulse response where we are having a 64 or 65 number of coefficients. So we have taken the more number of coefficients. So however, you can see this one is more closer to ideal or rectangular window function. Okay, however, if, or you can say if we have increased the duration of the rectangular window, what is happening? This transition width is reduced compared to this. If we compare these two, the transition width is reduced. So anyway, I think I should stop now. Thank you very much.